Hello friends, welcome to the mathematical room once again. I am the caretaker. So today we will see the binomial theorem. Now before going to the binomial theorem, let's just have a quick look at the meaning of this symbol. Now many of us have seen this symbol many times and we have used this capital sigma. It is actually called summation. Okay, this symbol represents a sum of what? Let's see what is given here. So m and n are non-negative integers. They can be in general integers also, but more commonly they are non-negative integers. Now for each integer I, there is a real number ai. So for example, these are all real numbers. A minus 3, A minus 2, A minus 1, A0, A1, A2, A3, etc. These are all real numbers. Okay, they belong to the set of real numbers. Okay. Now, we don't really need this part. Anyway, what does this symbol actually mean? If m is equal to n, okay, then this symbol just simply means m. Okay, just one term is there, m is equal to n. So in this case, the summation becomes ai. I is varying from m to m itself, and this is equal to nothing but am. But if m is less than n, okay, then this symbol represents this sum, am plus 1 plus am plus 2, like that it will go, plus a n minus 1 plus an, that is until till it reaches an. So for example, if I have summation ai where I is varying from, not that m and n have to be non-negative integers, but they can be any non-negative integers. Okay, say I am taking m equal to 2. If I take here 2, then I get only a2. But if instead of 2, for n I have say 10, okay, I varies from 2 to 10, then this sum becomes a2 plus a3 plus a4 plus a5 plus a6, 7, 8, 9 and 10. Okay, so that is the usual meaning of this symbol. But there is one more situation which is often not mentioned, but that is quite helpful to make things more compact. That is the situation when m is greater than n. In this situation, we generally avoid mentioning this symbol, but it can be mentioned provided we define what it means. Okay, so in this case, this symbol is defined to have the value 0. Okay, which means that if I start with something, say 3, but then on top of this I write a smaller number, then this is defined to, by definition, this is equal to 0. Okay, so this is the meaning of the summation symbol. It is used to write a finite sum in a more compact manner. Some people also call it finite series. Now we will use this to write the statement of the binomial theorem. Now, but before we go to the binomial theorem, let's just have a look at some formulas which we already know, which we have known since our elementary school, say 9th or 10th standard, even 8th standard. For example, I have let A and B be two real numbers. Okay? Let's just look at these expressions. A plus B whole to the power 1. This is nothing but A plus B itself. Then A plus B whole square. This is arguably the first formula which a student comes across when algebra is introduced. So this is A square plus 2AB plus B square. Then A plus B whole cube. For this also we know the formula. A cube plus 3 A square B plus 3 AB square plus B cube. But as we go to higher and higher values of this exponent, the formulas become more and more complicated, and after some point we don't really know by heart the formulas. We have not needed them with such high values of exponent so far. Okay, for this we will struggle a little bit to remember a formula if we have ever come across any such thing. Instead, what we do, we carry out the multiplication and we write this as a product of these two. If you want, you can write this as A plus B times A plus B whole cube. That way also you can do. So for this we already know the expansion AB plus B square, and for the second one, which is the same, A square plus 2AB plus B square. Now we carry out the multiplication. So first we multiply by A square, so A to the power 4 plus 2A cube B plus A square B square. Then we multiply by 2AB, 2A cube B plus 4A square B square plus, what will this be? 2AB cube. Finally, we multiply by B square. That gives us B square is the same as A square B square plus B square and B give us B cube plus finally B to the power 4. Now there are some terms which are which are similar. For example, this A square B square, A square B square, 4A square B square, they can be taken together. So we write it systematically. We start with A to the power 4. Then you can see one pattern in which we have written these terms. Here the exponent of A is 1. You can imagine the exponent of B, but that is 0. Here the exponent of A is 0, exponent of B is 1. Okay, because B to the power 0 and A to the power 0, they equal 1. You may wonder what will happen if one of these become equal to 0. Shall we have a problem like this? Actually, this is not a problem. In some texts, it is kept undefined, but we can define it to be equal to 1 and no problem occurs. Okay, we can define this symbol to be equal to 1, and you will see that everything goes smoothly. Okay, that thing we will assume. So that's why we have not mentioned A and B are non-zero or anything like that. Okay, this simplifies many things. Now, the next, here also you can see A square is actually A square times B to the power 0. Okay, AB is A to the power 1, B to the power 1. B square is A to the power 0, B square. So what is the pattern in which we are writing these terms? You see, we start first with A. Actually we start with AB, but the exponent of A is the same as this exponent. Exponent of B, to start with, it is 0. Then the exponent of A will decrease one by one, and that of B will increase. In what fashion? So that the sum of these exponents all are equal to this exponent. You see, 2 plus 0 is equal to 2, 1 plus 1 is equal to 2, 0 plus 2 is equal to 2. So it's just the number of ways you can write 2 as a sum of two other non-negative integers. Here also you see 1 plus 0 is equal to 1, 0 plus 1 is equal to 1. So in this same fashion, the next one, A cube is actually A cube times B to the power 0. Then you see exponent of A is decreasing and exponent of B is increasing. From 0 it has become 1. Then here it has decreased further. From 2 it has become 1, then next it vanishes, means its exponent is 0. But for B it is increasing. Here it is 0, here it is 1, then 2, and then finally 3. So this is the fashion in which we are writing. So that's why we start with A to the power 4. Then we will see where we have A cube B. So here we have 2A cube B, another 2A cube B. So these two are A cube B's. So they give us 4A cube B. B means B to the power 1. Then the next one will be exponent of A will decrease by 1, exponent of B will increase by 1. That means A square B square. So you see A square B square, A square B square, 4A square B square. That means plus 6A square B square plus. Then in the next one will naturally be A B cube. So A B cube is, you see this one, 2A B cube and 2A B cube. That means 4A B cube plus finally B to the power 4. There is only one B to the power 4. So plus B to the power 4. I just want to go one step further by finding the expansion of this one, A plus B whole to the power 5, so that things become much more clear. So here also we don't know any formula. I mean, if someone knows, they may know, but I don't know the formula by heart. So what we do, okay, we can write like this. Then we will have to carry out the multiplication and then accordingly arrange the terms. So for this one, I already have the expansion here. So A to the power 4 plus 4A cube B plus 6A square B square plus 4A B cube plus B to the power 4. Now I calculate the product. First I multiply by A. So I have A to the power 5 plus 4A to the power 4. The exponents of A's will just increase by 1 since I am multiplying by A, that's all. Plus 6, we have A square B, it will be A cube B square. I mean A square B square we had. Plus 4 A square B cube plus a b to the power 4. Okay. Plus then I multiply by b. So b I am writing on the right hand side so that we can recognize the similar terms afterwards. So here a to the power 4b plus 4a cube b square plus b times this 6a square b cube plus b times this 4a b to the power 4 plus finally b times b to the power 4 is b to the power 5. Now again we write these terms by collecting similar terms together and writing them in the fashion like we have been writing. Okay, so a to the power 5 plus, okay, next a to the power 4b, 1 and another term, 5a to the power 4b. Then the next one is a cube b square. So 6a cube b square plus 4a cube b square gives me, they give me 10a cube b square. Then a square b cube, 4a square b cube, 6a square b cube, 10a square b cube plus a b to the power 4. This one, 4 plus 1, so plus 5a b to the power 4. Finally, b to the power 5, there is only 1, so b to the power 5. Okay, so we have got expansions up to the 5th power, right? Now, what are we observing here? You see, the pattern in which the powers of a and b are going, that we already know. The powers, the exponents of a will decrease, simultaneously the exponents of b will increase, so that the sum of the exponents becomes this one, this number, this index or exponent. You can see here 3 plus 0 is 3, 2 plus 1 is 3, 1 plus 2 is 3, then 0 plus 3 is 3. Here also 4 plus 0 is 4, 3 plus 1, 2 plus 2, 1 plus 3, 0 plus 4. Here also 5 plus 0, 4 plus 1, 3 plus 2, 2, 3, 1, 4, 0, 5. That we understand. But what about these numbers, these coefficients? 1, 1. Here we have 1, 2, 1. Then here we have 1, 3, 3, 1. The next one we have 1, 4, 6, 4, 1. Finally 1, 5, 10, 10, 5, 1. So how do we know about these exponents? Okay, that is the thing that we have to decipher now. So let's write down the, or sorry, not exponents, I mean the coefficients. Whatever is there in front of these variable looking numbers, they are called coefficients. Okay, if we can remember these things. Let me just write the numbers for the 5th expansion here. We have 1, 5, 10, 10 and 1. Okay, now I'm going to wrap this up. And I will write the coefficients here in a visually appealing manner. First we have 1, 1. Okay, 1, 1. Then 1, 2, 1. 1, 2, 1. After that I have 1, 3, 3, 1. 1, 3, 3, 1. Then after, why I am writing this in this pattern, we will see soon. Then we have 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. And then finally 1, 5, 10, 10, 1. 1, 5, 10, 10, 10, 10, sorry, I think I have a 5, I had a 5 here, yes, 5, 1, okay. Now this pattern emerges, but what is this pattern? You can see the exponents of course can be written here. This is for 1, this is for 2, second row, this is for 3, so 4, and this is for 5. We start with 1 and 1, okay, that is, they are fixed. And in the outer part of this triangular pattern, it looks like a triangle, isn't it? Outside of this triangular pattern, we have 1, all 1s. Inside, we have some numbers. What are the numbers? You can see that if you add these two numbers, 1 and 1, you get 2. So any number that is occurring inside of this, in the interior of this triangle, okay, if we call them so, each such number is the sum of the numbers above it, which are closest to it. You see, here this 3 comes from 1 and 2. 1 plus 2 is equal to 3. Similarly, 2 plus 1 is equal to 3. 3 plus 1 is equal to 4. 3 plus 3 is 6. 3 plus 1 is 4. 4 plus 1 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. Now we have expanded till the 5th power. If we expand the 6th power, shall we get the numbers in the same pattern? It happens that we continue to get the numbers in the same pattern, but this is just an observation, okay? We have observed something till the 5th power, and we are guessing that the same pattern holds in general. For that, we of course need a proof. And by the way, at this stage, this pattern that we have recognized here, it is somewhat still complicated in the sense that to write the expansion of the 6th power, say a plus b whole to the power 6, you have to know the expansion for the 5th power. So this pattern is the numbers you will not get the numbers directly just from this number 6. You have to generate the numbers recursively. That is, first you generate the numbers of the second one from the first one, then generate the numbers for the third one from the second one, and so on. Okay, so that is one problem. But if what we are thinking holds generally, then the expansion of this should look like this. See, the way to write this is this. First, let me ignore the numbers. Let me just write the powers of a and b. We will have a to the power 6 plus a to the power 5 b plus, I am keeping some space for writing the coefficients or the numbers. Then a to the power 4 b square plus a cube b cube plus a square b to the power 4 plus a b to the power 5 plus b to the power 6. If what we are thinking truly holds, then the next row will look like this. 1 plus 5 is 6. 1 stays. We start with 1 and end with 1, right? So they are always there. So 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. Then again 10 plus 5 is 15. and finally this is 6. So the expansion should look like this. 1, we first of all have 1, then 6, 15, 20, 15, 6, 1. So this should be the expansion. We don't know, we are only guessing. Okay, this turns out to be the expansion, but we have to do better. We have to recognize these numbers in some other way, not in this way where we need whatever we have before these numbers, we need all of them, not in this inductive fashion or recursive fashion. We need the numbers just from this 6 and where the numbers are appearing in this expansion. You see, you can treat this one as the first term, a to the power 6, then a power 5 times b, this is the second term. So from that position and this exponent, we have to know the numbers. Okay, here comes the things which we have seen so far, combinations. You remember NCR. NCR we have seen, this is the number of ways we can choose n objects by taking r at a time. Okay, number of ways of forming groups of r objects from n objects. So these numbers, and if you recall this notation, apart from this, we also write them like this. Okay, n above r, and they are enclosed within round brackets. If you recall, they are called binomial coefficients. These numbers. And this is the reason, because these numbers which are appearing as coefficients here in these expansions, these are nothing but these numbers. Let us see how. Okay, and this triangular structure that we have written, where we have these numbers, this is called Pascal's triangle. Okay, now we need to recognize the numbers. First we have 1, 1, right? Then we have 1, 2, 1. Now 1 can be thought of as 1C0. Not just thought of, it's the same. Okay, 1C0 equals 1. 1C1 also equals 1. You can, I leave this to you. You go back to the definition of NCR. NCR is nothing but n factorial divided by n minus r factorial times r factorial. You go to this definition, put the values and see that these are the results. Okay, this one, 1C, again, 2C0 is also 1. 2C1 is 2. 2C2 is 1. What were the next things? 1, 3, 3, 1. 3C0 is 1. 3C1 is 3. 3C2 is also 3. And finally 3C3 is 1. Okay? 4C0 is 1. So anything C0 actually becomes 1. 4C1 is 4. And anything C1 is that thing. 4C2 is 6. 4C3 is again 4. 4C4 is 1. Then let us write one more row. 5C0 turns out to be 1. 5C1 is 5. 5C2 is 10, 5c3 is again 5, 5c, sorry, this is 10, this is again 10, this is 5, and finally 5c5 is 1. To see that this is really the case, let me just take one binomial coefficient at random and let me see whether this is actually true. Let's calculate 5c3. Okay, 5c3 is 5 factorial divided by 5 minus 3 factorial times 3 factorial. So this is 5 factorial divided by 2 factorial times 3 factorial. Now 5 factorial can be written as 5 times 4 times 3 factorial. 2 factorial means 2, and here we have 3 factorial. So these two cancel out and we get 10. So this is actually correct. You can verify that all of them are correct. So from this we get the pattern. What is happening here? You see, let me take this one so that I have some terms and at the same time I don't have many terms to write. Let me wrap the other parts off and let me try to recognize the cube of a sum in terms of this binomial coefficients. I have a plus b whole cube is equal to a cube plus 3 a square b plus 3 a b square plus b cube, right? Now I can write these numbers as binomial coefficients. 3c0 a cube plus 3c1 a square b plus 3c2 ab square plus 3c3 b cube. Do I get a pattern now? You see, here I should have written b to the power 0. Here a to the power 0. Okay. Now this part, this 3 remains 3. Okay, there is no change. In NCR, 3 remains fixed, n remains fixed. So this one is 3. Now I want to write this as summation, but before that, let us see the pattern. What is happening here? The exponent of b, here it is 0, here also it is 0. Here it is 1, here also it is 1. So I can recognize this number below c as the exponent of b. And since I already know from the exponent of b, I can calculate the exponent of a. Why? Because their sum should be equal to 3. So if it is 0, this must be 3. When it is 1, this must be 2. When it is 2, this is 1. And when it is 3, it is 0. So from the exponent of b itself, I know all the numbers that are varying in this sum. 3 remains fixed, that is fine. So now I want to write this as a summation. Since this is a sum, so I can write this as a summation. What is varying? Since I am recognizing everything using exponent of b, so I put the variable over b to the power I. Now I will change. I is changing from where to where? I is changing from 0 to 3. 0, 1, 2, 3. Okay, so I is changing from 0 to 3. 3ci. See, 3c0, 3c1, 3c2, 3c3. And the exponent of a should be such that the sum of this and this should be equal to 3. That means this will be 3 minus I. See, 3 minus 0 is 3, 3 minus 1 is 2, 3 minus 2 is 1, 3 minus 3 is 0. So this is the expansion of a plus b whole cube written in a more compact form. Of course, this and this are the same thing, but this is writing it in a more compact form. Now let us write that one also in this same fashion and see whether we get something similar. We will get something similar, but let's just do it. So what is it? A plus b whole to the power 4. So if you look at it,